Good afternoon. Here is Mr. Vladimir Lopatin. I represent Scientific and Educational Center Kачество. My specialization is ultrasonic testing. First, I would like to take a closer look at the theoretical aspects of the ultrasonic testing. We will try to find out what contributes to significance of this method of testing. Ultrasonic testing is one of the main testing methods that allows detecting both surface and subsurface flaws. Ultrasonic testing is based on elastic vibrations, which make it possible to detect flaws and discontinuities. There are certain regulatory documents for each type of an object to be tested. This video is dedicated to the testing of welds. Therefore, we will use State Standard 5574 as a basis for ultrasonic non-destructive testing. This is the main document, which includes both technologies, principles, and techniques of testing. However, the rejection rates are associated, as a rule, with the production sector and line of industry the object to be tested belongs to. In particular, if boiler and pressure vessels are to be inspected, regulatory documents on such test objects are used. For example, ST0083 Gazprom Company Standard. It is to say that each particular type of objects to be tested requires specific regulatory documentation. That is, particular type of objects to be tested has its own rejection documents, which determine what is acceptable and what is unacceptable. I would like to draw your attention to four main techniques used for rejecting a part. The amplitude technique considers excess of the amplitude over the rejection level. The next technique is the extent of the flaw. The third technique is the number of defects and a certain distance. The fourth technique is the total length of small flaws. Depending on the type of the object to be tested, there are their own rejection standards. A number of equipment is required to implement ultrasonic testing. First, an ultrasonic flow detector processes and emits ultrasonic waves. The next device is a piezoelectric transducer containing a piezo plate, which provides the emission of elastic waves propagating in the part to be tested. Moreover, at the same time, in addition to emitting waves, the same sensor receives the reflected ones. Reference samples help to perform testing of parts and products. They are divided into two main types: measures or standard samples and tuning or reference samples. Depending on industrial sector, appropriate reference blocks are chosen concerning the material and taken into account the rejection standards the regulatory documents consist of. To carry out ultrasonic testing, ultrasonic flow detector must be set up first. This process consists of two main stages. At the first stage, the necessary parameters are adjusted, and then the device is set up concerning the material the product is made of. There is a certain algorithm for setting up an ultrasonic flow detector, which consists of a number of issues. First, depending on what material we are to test, the speed of the ultrasonic waves is adjusted. If we look at the screen, the speed is 3260. This is the speed of the shear waves, because we have to use this type of waves at the angle entry of the ultrasonic waves. Such speed for steel equals 3260. After that, we set up the angle of the transducer we are using. The transducer is also called the probe. Go to the transducer or probe tab, set the input angle, which is marked on the transducer. Here it is 65 degrees. As you can see it on the screen, the angle has already been set. If it is required, the angle might be changed manually via the device menu. After that, the scanning pattern is set. As you can see it on the screen, again, there is one cable, then there is one plate inside, which both emits and receives ultrasonic waves. It is so-called combined scheme. Therefore, we set a probe type as a single-element transducer. After that, you need to reset the protector. That is, we adjust the depth gauge. It should be 0. If we are going to use the DAC, we must reset the DAC points to adjust this block later. This is a temporary sensitivity adjustment. After setting above-mentioned parameters, we move on to setting up the flow detector, which consists of 4 main steps. First, we set up the flow detector sweep. A flow detector, roughly speaking, is a stopwatch. When we start it, the time is displayed on the horizontal axis. Time of the ultrasonic wave transit depends on the distance at which the reflected signal is received. Here, the sweep is set. If a direct transducer performs the testing, 2 thicknesses are to be taken in account. If we use an angle beam transducer, then count 7 thicknesses. So we are able to detect the signal reflected from the discontinuity. The next parameter to be adjusted is the depth gauge. The depth gauge is adjusted to the reflector at a known depth. For example, here is a sample, in other words, a passive instrument, previously known as CO3. This is a standard sample that has a distance of 55 mm. This means that the radius of this sample is 55 mm. If we install the transducer on the surface of this sample, we will see on the screen the reflected signal from the opposite side plane. If a path equal to 55 mm is observed, the depth gauge is set up. In our case, they are 54 mm. In order to clarify this value and make it accurate, there is a parameter called the wear plate. By changing the parameters on the wear plate, we can adjust the appropriate value of the path. So, if you look at the screen, the required value of 55 mm is set. The depth gauge is adjusted. The next setting is sensitivity. Sensitivity is a flow size, which will be a sign for rejection. Everything that has a value of signal exceeding this one in amplitude will be considered defective. This parameter is configured according to the reference document, which regulates a testing process as a whole. In accordance with this document, a reflector in the form of notch is designed. The reflector may be of another type. There are 4 main types of reflector. These are flat-bottomed hole, side-drilled hole, segmental reflector, and notched reflector, or an angle reflector. Depending on the purpose of testing and thickness of the part to be tested, the size of the angle reflector is chosen. Under industry-specific construction standards, the size of the angle reflector equals 2 by 1.5 for a thickness of 10. Next, we adjust the sensitivity. Since welds are checked with a straight and once reflected beam from both sides of the weld, we must ensure that the depth sensitivity is the same. Due to the fact that the wave is attenuated, We must ensure that the signal, no matter how deep it is, has the same amplitude. We take a transducer, install it on a sample surface, and search for a flaw located on the opposite surface, that is, at a depth equal to the thickness of the sample. The next step is to determine its size and location. There is a formula for calculating the depth. This is the distance L, equal to thickness multiplied by the tangent of the angle alpha minus n. If we install the reflector at this distance, we will definitely see it. When a surface is too wide, the power of signal in the opposite direction is significant. So, to detect a small notch, the gain of the signal is to be increased. The gain is adjusted using the Gain menu tab. On the screen, you can see the gain value is growing. The transducer is installed opposite the notched plane. You would observe a signal from the notch on the screen. If I move to one side of the notch, the signal disappears. The same happens when I move to the other side of the notch. Accordingly, we caught the reflection from the notch. Our next task is to ensure that our signal reaches the rejection level. There is a sling here. It is a service signal. We increase the sensitivity, that is, the gain, to the rejection level. So we received a desired value. As it was mentioned earlier, the sensitivity needs to be aligned, so we must use the DAC unit. You could notice it on the screen. We detected the reflector. This is so-called initial point or first signal. Moving around the screen, a point is to be set, so that it is opposite the maximum. We change the mode and restore the maximum signal. The initial DAC point is set. As it is seen, the value of the signal reaches 58, 57 decibels. We input a value opposite it and set the gain. 57 decibels is our rejection level. We register this value in the test report. We will record that H rejectable equal to 57 decibels. Now we must catch the reflection from the opposite side via once reflected beam. Now the second notch located on the surface to be tested is clearly observed. We install the transducer opposite the notch, move along the surface, searching for a signal from the notch. The signal is now detected. We are to find it on the screen. Here is our notch. We are to achieve the maximum, because in ultrasonic testing, it is a common practice to perform all measurements at the maximum signal. Our second point is found. We look at the screen and add the second point. The time is adjusted, so this is the location of the point. Moving around, we achieve the maximum with a lower gain. That is, the gain of the DAC. We adjust the signal to reach the rejection level. The notch located on the straight beam and the signal beam corresponds to our value. As a result, we have adjusted the sensitivity. The fourth setting that needs to be adjusted is the inspection area, where a flaw in the weld can be located. It can be located at an area from the bottom, or rather, from the transducer pulse to a signal beam on the surface. If the transducer is being moved along this line, the service signal is detected. This is the inspection area. Watching the pattern on the screen, we are to find the beginning of our signal and shift to it, the probing one. But be careful to avoid false alarm for flaws. So the area where the inspection starts is determined. Next step is to determine where the inspection ends. This would be the notch reflected once. We determine the width of our signal and change it. It is required that the maximum remote signal hits previously defined area. We marked the inspection area. Adjustment of the flaw detector is completed. Since this transducer is new, its parameters are known. Nevertheless, it is better to make sure they are correct. And since there are tolerances for any transducer, in particular for an angle, for probe index, and so on, we must definitely check the parameters of the transducer. The parameters of the transducer are checked on two CO3 samples with the use of which probe index is defined. A reference sample of this type has already been used to adjust the depth gauge, that is, moving along its surface. We are to reach the maximum signal on the screen. Then we are able to detect the signal index point opposite zero, which helps us later to determine the probe index. The probe index is the distance from the front face to the index point. This value is required firstly to calculate the scanning area, and secondly to determine the parameters of the detected flaws. The index point is determined. The next transducer parameter to be identified is the angle of probe. The task is to determine the angle of the wave propagation. This requires a CO2 sample. There is a control reflector with a diameter of 6 mm, so we found probe index. Moving along the surface of the sample, we watch the screen looking for a signal. This way, the maximum signal is found, and accordingly, opposite the maximum signal, we see an angle equal to 65 degrees. We determined that this transducer complies with the standards. Tolerance for angle is 2 degrees. In case of worn-out transducer, resulting in loss of contact with the surface of a certain roughness, it is not allowed to use this transducer. The next parameter that must be clarified for our transducer and flaw detector test system is the dead zone. If we take a look at the sample, there are two 2 mm drilled reference reflectors. One of them is drilled at a depth of 3 mm, the other at a depth of 8 mm. We are to define a dead zone on these holes. I've installed the transducer upon the sample and moving along its surface, watch the screen of the flaw detector. The signal I detected has a resolution. It means that it is visible on the screen of the flaw detector. The dead zone is less than 3 mm. If this signal cannot be detected, for example, in case of high level of noise, we had to move to the second reflector. It is located at a depth of 8 mm. A coupling media was applied. In this case, it is oil. You can choose any other media. It was not mentioned before, but application of the coupling media is essential for testing, because the ultrasonic wave entry is impossible without it. We move along the surface and see that the reflector is detectable at a depth of 8 mm. Moreover, it turns out that if we had not found it there, the dead zone would have been less than 8 mm. Thus, all the parameters of the piezoelectric transducer are defined. After the flaw detection system is set up, we proceed directly to ultrasonic testing. Here we have a test specimen, an object to be tested. We have all the necessary parameters: thickness, width of the reinforcing bead, type of welding, and reference documents. We set up the system using our notch. Now we need to calculate at what distance we need to move the transducer to provide scanning from both sides via a direct and once reflected beam. The following formula is to be used. L is for the maximum distance that the transducer must cover by a once reflected beam, and it equals two thicknesses multiplied by the tangent of the alpha angle minus n. The thickness of our transducer is 10 millimeters, so two thicknesses is 20 millimeters. The tangent of an angle of 65 degrees is 2.1. We subtract the value of the probe index, which is 7, we measured it earlier, and we get 20.41 minus 7. We set an area. That is, it is necessary to shift the transducer by the value of this area. In our case, it has a value of 36 millimeters. So we set the transducer to provide a distance of 36 millimeters from the index point. This means that testing is carried out at a speed of no more than 100 millimeters per second, because human eye needs some time to catch the signals appearing on the screen of the flow detector. Secondly, we need to ensure a certain movement of the transducer across the weld with a certain step by swinging the beam by 10 degrees. In this case, the scanning pattern is called transverse longitudinal. First, we shift the transducer across, then we provide a scanning step and turn it back. We rotate the probe all the time to detect flaws of different orientations. The offset must be no greater than half the size of the plate width. If we look at our plate here, the width is 8 millimeters, so the step should be no more than 4 millimeters. We have determined all the main scanning parameters: speed, step, and inspection area. As it was mentioned, all measurements during ultrasonic testing are performed at the maximum signal. So we keep moving the transducer as the scanning scheme requires. On the screen there are two zones set: a rejection level equal 80% of the screen height highlighted with a red marker. The line below is the so-called control level, on which we measure the flow. This level is 2 times less. This is 6 decibels. It is equal to 40% of the screen height. So testing starts. While moving the probe, we carefully look at the screen, waiting for something to appear. If some signals appear on the screen, it is advised to shift to this point. Here, as you can see, a huge signal appeared on the screen. So we found something in the sample. As it was already said, we are looking for a maximum signal. Here we have received the maximum signal on the screen. I remind you that H rejectable is equal to 57 decibels. You could see it. It is set. We are to make sure that the signal reaches our rejection level. Here it is equal to it. The value turns out to be 51 decibels. So the difference between actual signal value and rejection level is 6 decibels. We are to record the delta value. It means that the signal found exceeds the signal that arose from the notch by 6 decibels. We go back to the initial value and measure the flow depth at a maximum point. It is equal to 3 millimeters. It means that the maximum signal is at the depth of 3 millimeters. Next, we need to find out what is the extent of our flow. To do this, we set 57 decibels and move the transducer along the flow in one direction and in the other towards its beginning. It is to ensure that the signal starts to fade. Don't forget to turn the transducer by 10 to 15 degrees, looking for the point where the signal reaches our control level. This point is right on the verge of a blue line. Using a ruler, we analyze this distance between a flow and a 0 point. In this case, it is 35 millimeters. The distance from 0 to the middle of the transducer is to be measured. This is the beginning of our flow. It's Z coordinate of the beginning. We keep moving the probe along the flow, and now it has become obvious that the flow found is the extended one. Here the signal starts to fade. Distance Z is reached. To measure the length of the flow, we use the ruler again, and look, the value is 75 millimeters. In our case, Z coordinates are 35 millimeters at the beginning of the flow and 75 millimeters at its end. Thus, we have determined all the parameters of the flow. The excess in amplitude is 6 decibels. Depth is 3.5 millimeters. The flow starts at 35 millimeters and ends at 75 millimeters. That is, delta L, the length of the flow, is 40 millimeters. That is, we have determined all the parameters of the detected flow. Further testing is carried out similarly throughout the whole surface of our product. Thank you for your attention.